Well, good evening, everyone. Tonight we have Sean Gavin as our speaker. He is a theoretical nuclear physicist and a full professor at Wayne State University, professor of physics. His research involves interpreting ultra-high energy collisions of particles at the Large Hadron Collider in Geneva, Switzerland, and the Relativistic Heavy Ion Collider in New York. What happens in these high collisions mimics what happened in the first fraction of a second after the Big Bang. He lives in Plymouth, Michigan, originally from New York. He enjoys his family, running, and science fiction. His title tonight is How a Collision Between Darwin and Lord Kelvin. I don't think that happened in the Large Hadron Collider. Sort of gave rise to modern cosmology. What a title. Sean?
Thank you. Thanks for the nice introduction. So I hope you can hear me. This is sort of a talk about the history of physics, and it's a talk about the history of a lot of stuff involving astronomy. I'm neither an astronomer nor a historian, so I'm pretty much going to be making stuff up. So if you don't mind. And trying to turn on my pointer is a new challenge. So the story starts with Charles Darwin. Charles Darwin is arguably one of the greatest scientists of all time. He's certainly set the stage for modern biology with his idea of evolution by natural selection. Here's Darwin as a dapper young man. Here he is at the age of 45, about the point where he's publishing The Origin of the Species. And here he is as a great sage, no tea, beer, recurring theme in this talk. Now, his idea of evolution starts with says that similar species descended from a common ancestor is possibly extinct through a gradual process, and his mechanism is natural selection. Here are the famous Darwin finches, which he would eventually realize became specialized because they were separated in space and eating different types of foods and singing different songs and eventually becoming distinct species. Now, experiments are able to demonstrate in the laboratory today that this kind of mechanism works. If you start with a sample of fruit flies and feed one of them starch and another one maltose, over time, they eventually evolve to become separate species that will no longer be able to breed. And in humans, we find this kind of stuff taking place too. The lactose tolerance, the ability to digest milk, is something that has come from Turkey spread throughout Europe over the course of around 20,000 years, just in time for the agricultural revolution to take advantage of the energy that comes from milk. And that gives you an idea of and since not all humans are lactose tolerant, you can see that 20,000 years is not enough time for evolution to really run its course and make a significant change in the population. In fact, the fossil record implies that it takes millions of years for evolution to take place. That's very important for this talk. Now, Darwin started out as basically a geologist, and at the time, the evidence of work was that geological forces act over very vast time scales. At the time, when Darwin was young, they were beginning to discover the first dinosaur bones. Behind the background here is an iguanodon discovered in 1824. In accord with this idea that there had been older animals that were completely different from the modern animals, the idea came forth that geology was taking millions, billions, trillions of years. They didn't know how long. And they came up with the idea of uniformitarianism, which was the idea that basically natural processes in the past operate just exactly as they do now. There's a steady state of volcanism, sedimentation, and erosion sort of cycling things around, and this has gone on as far as they could tell indefinitely. Now, Darwin, when he started to market his theory of evolution, he realized that it would be important for him to have enough time for these biological changes to take place. And so he wanted to make some quantitative evidence in the organic species to support this, to support the idea, the slowness of these processes. So he looked at a nearby area called the Weald, which is in southern England. That's not far from where London is. The Weald should look like a nice big hill, but instead it's sort of chopped off in different layers, and you can see, he could see that there had been a substantial amount of erosion, and he estimated that it would take about 300 million years for such erosion to take place. Now, here's an important thing about Darwin that you have to know. Darwin was very bad at math. He liked finding fossils and birds and things like this. He was brilliant when it came to that sort of thing, but he was not very good at math. He tried to learn, he was never very successful. And his estimate of 300 million years, even at the time, was known to be not very good. Modern estimates put it at 20 to 30 million years for the Weald. Now we get to the major argument of the first half of this talk. Darwin is saying that evolution may take a lot of time, but geologists agree that the Earth is very old. In comes Lord Kelvin, who's a physicist. He says that physics limits the age of the sun and the Earth, and he disagrees fundamentally with Darwin. Okay, and notice here that his theories, these guys, they're pretty good. They're both very important physicists. So are scientists. So Lord Kelvin, born William Thomson, it's established the Kelvin scale of absolute temperature, among many other things I'll talk about. He was so revered as a scientist in his time that he's buried in Westminster Abbey next to Sir Isaac Newton. Okay, so he was one of the most famous scientists in his time. He's not really all that famous, and he's not really in the top 10, I would say, of most modern physicists. So the question is, how did that actually happen? Well, first about the man, okay, and his works. He invented and proved Stokes' theorem. There's got to be a story there that's called Stokes' theorem. Anyway, he sent it in a letter. This is the way he wrote it down. He sent it in a letter to Stokes. Stokes made it famous by putting it in an exam in Cambridge University. And it's not known whether anybody was able to prove the theorem. But in any case, that was the first publication of the theorem. So it's named after Stokes, but it's really due to Kelvin. And anyway, this is how Kelvin wrote it down. What a mess that is. And now it's quote unquote simplified into this form. You could write even simpler forms of that. Anyways, math. So then he applied a lot of this math to electromagnetism and early fluid mechanics. And he was basically widely acknowledged as a mathematical physicist. But In addition to that, he was a very important character in the Industrial Revolution. He invented a lot of different things. One of the things he was most known for was that he guided the construction of some of the first transatlantic telegraph cables. Now, in those days, they didn't know anything about electromagnetic theory, so what they would do is just take a cable and put a large voltage on one end and hope that something comes out the other end. Now, there's going to be a problem with that, putting a big cable in salt water, okay? Because you know about sparks, fish, and things like that. So he had to figure out how to do it, how to get a signal on the other end, and how to read a very, very sensitive, very small signal that was coming out the other end. And this he did figure out, and they made it work eventually after a couple of tries. And his inventions led to great wealth, and it led to him becoming knighted, and also just capturing the public imagination of this great scientist coming up with things that were revolutionizing the world. But, you know, maybe physicists know him most for his work on thermodynamics. You know, this is where the temperature scale came from. He worked on the first law of thermodynamics, which basically said that energy is conserved. He worked with Joule on his experiments. He was sort of providing theoretical guidance for Joule when Joule was figuring out proving this stuff. And then he was one of the inventors of the second law of thermodynamics. So the first law of thermodynamics says that energy is conserved. You can't put more work. You can't get more work out of an engine than you put in terms of heat energy. And the second law says that if you're using heat energy to turn into mechanical energy, you're going to lose something, and you can't even break even, as we say. Now Kelvin is so famous for this that there's a brand of refrigerators that's built in Detroit that's named for him, the Kelvinator, and this is, I think this is a reproduction of them, so you can still get them somewhere. I think they're so efficient, but it's nice. So Kelvin realized, based upon his work in thermodynamics, that there could be no perpetual motion. So even when he was a very young person, he realized at once that what this meant was that the sun could not be eternal, the earth could not be eternal, and in fact the universe, even the universe could not be eternal. Eventually we reach a heat death in which everything just turns into entropy. And so Kelvin asked very profoundly how long do these things live? And he sought a scientific answer. One of the first to do that. And so he set about this very methodically, very meticulously, and he first turned to figure out how long the sun would last, and so he figured, what's the source of the sun's heat? And he considered three possibilities. One is that the sun burns some fuel that will eventually run out. Two, that it's continuously supplied by an external energy source. And three, gravitational contraction. Okay? Now Kelvin dismissed the first one, even though that's the correct one, because he knew of no fuel that could possibly work. So when you look at chemical reactions, and is the sun burning? Kelvin thought, as did all scientists at the time, that the sun would be made out of the same stuff that the Earth is made out of. And the Earth is made out of rocks, so the sun should be made out of rocks, but they're burning rocks. So if the sun is made out of burning coal, he estimated, based on the total light that he could see coming out of the sun, that the sun could only last 10,000 years. And it turns out that today, if the sun was burning hydrogen somehow, and with the correct emission rate, which includes ultraviolet, infrared, stuff that was invisible to Kelvin at the time, you get again 10,000 years, and 10,000 years is not a lot of time. So the sun can't be burning chemicals. So his first idea, which he stuck to for quite a while, about 10 years, was could the sun, could a constant rain of meteors on the sun maintain the sun's heat? He liked this because it meant that the sun could be eternal, or it would last a very long time based upon wherever the stuff is coming from. So, and it also was based on this conversion of mechanical to thermal energy, which is right up Kelvin's thermodynamic alley. Okay. The problem is that this disagrees with experiment. If there were, he needed a certain amount of matter to be flowing into the sun, and if that much mass was in between the orbit of Mercury and the sun, then it would so disturb the orbit of Mercury that this would be visible from the Earth. Okay? And they had good measurements at that point of Mercury's orbits that were good enough to sort of prove that Kelvin's meteor rain hypothesis couldn't possibly work. So he finally came up with this idea, which is the one that he stuck to. He said that which is the gravitational squeezing of the sun. The idea is that the sun, light and heat energy is coming off of the surface of the sun, which means that the sun is cooling. So even if it's very hot within, the gas on the surface must be cooling off. And if it's cooling off, it's losing mechanical energy. So it starts to settle down a little bit more. And then that squeezes on the inside, which then pushes back and heats it back up and radiates more. But this will only go on until eventually all of this energy is lost and it's contracted as much as it possibly can. But this is quite a lot of energy because the sun is a big, heavy thing. You can estimate from this, the energy is given by the Newton's constant times the mass of the sun squared divided by the radius. There's some 3/10 in there that comes from math. And then he takes this energy from the gravitational contraction, divides that by the observed luminosity of the sun, and gets an age of 200 million years. And this is Kelvin's maximum age for the sun. 20 million, what did I say? 200. 200 million. I'm wishful thinking. See, that's, but not 200 million. It's still 20 million. So, sorry. That's right. Yeah. That's exactly. So Kelvin says. So Kelvin says basically in this paragraph, it's who are you going to believe, me or your own eyes? He looks at he measures the sun's age to be 200 million years old. Darwin, on the other hand, says he needs 300 million years for the wheel to go away. And Kelvin says, what are we to think of such geological estimates of 300 million years for the denudation of the wheel? Basically, he says there's no way that can happen. And so the point here, there's 2 points. One is that he realizes not only does he realize that he's in conflict with Darwin and a lot of geologists, he's kind of going after him by name in the papers that he's writing. So there's an edge here. I sense an edge in the way he's interacting with people. Now, so from his 1862 page, his 1862 intro on the age of the sun's heat, he says that the second law of thermodynamics proves that motion is irreversible, the sun and the earth are not eternal, and the heat death of the universe is inevitable. And so he says that this means it is impossible to conceive either the beginning or the continuance of life without an overruling creative power. And now we get to Kelvin's motivation. See, he's really quite a religious fellow. I mean, he went to church every day. He was quite serious about it, and so he felt that this kind of work was, verifying his religious understanding of the creation of the earth. Right? He felt he was doing God's work, in other words. This is very important for the rest of this. So now the question is, what science was Kelvin missing? And of course, fusion is the real power source of the sun. Everybody here knows this, but I always want to put it in the time, the context of the time. In the period that Kelvin was alive, people had gone from thinking that atoms are maybe something to discovering radioactivity, electrons, and Einstein proposed E equals mc squared, the equivalence of energy and mass. And even Lord Rutherford, he had seen something. Rutherford's greatest discovery of the atomic nucleus was a little bit after Kelvin had passed away, but he had seen Rutherford and met with him and talked about the energy that was in radioactive decay in his later years. At the same time, people had been looking up at the sun. In 1890, Lockyer discovered that helium. He discovered the element helium in the spectrum of the sun. And in 1920, Eddington first proposed, this is now after Kelvin, that the fusion of hydrogen and helium can release energy from E equals mc squared. And Cecilia Payne-Kropotkin measured the sun's composition and in fact, the composition of many stars, and found that they're all just pretty much about the same, made of about 75% hydrogen and 24% helium. So their composition is very different from terrestrial stuff, and mostly hydrogen and a lot of helium. And then in 1938, Hans Bethe, the happy guy with the giant brain, is discovered the theory of fusion. Really makes it very concrete. So now fusion is 1,000 times more, can yield 1,000 times more energy per mass than gravitational contraction. And therefore, using this same formula 1,000 times, you get an age of 10 billion years, which is the currently thought lifetime of what the sun can be. And so what we now know is that fusion involves a combination of low mass nuclei into larger nuclei. Helium has slightly less mass, than 4 hydrogen nuclei, and the fraction of mass that you gain when you fuse together these four neutrons and protons into helium is released by E equals mc squared. So this gives you a much more efficient fuel. And the important thing is that Kelvin really couldn't have known any of this at the time. Okay, so you can give Kelvin a pass. He knew that if there was another source of energy, it could extend the lifetime of the sun, but he didn't know of it. So he was doing the best he could do based on his the science that he was aware of at the time. And in fact, the gravitational collapse is really what makes stars form in the first place. As the gas collapses from a dust cloud, it eventually Kelvin contraction heats up the core until eventually it becomes hot enough to spark fusion, and then this blows everything away. So the time scale that Kelvin estimates for the life of the sun is in fact the time scale it takes pretty much for this collapse to ignite fusion. Now, actually, where Kelvin, so I would give Kelvin full marks for his work on estimating the age of the sun, where he got kind of I would say, maybe not, where he started to cause problems was with his estimate of the age of the Earth. Because the thing was that he assumed that the Earth had to be made out of rock. And he measured the difference between the temperature down in mine shafts compared to the temperature at the top. And measuring this gradient, he could compute, and knowing what the thermal conductivity of rock is, he could compute how long the Earth would retain its heat from an initial molten state. And from the inferred rate of heat loss, and he did an extremely large amount of work to do this. He did his own experiments. He got friends to do more experiments. He did a lot of work, and he was using calculations that were the state of the art of theoretical physics. Solving the Fourier's equation. It was new stuff. And with this, he estimated that the age of the Earth was around between 20 and 400 million years. Now, the thing is that when he got that estimate, and that estimate was about the same as his age of the sun, you could see how the lights go off inside his head, right? He says, I've got it. This is right. There's like, I didn't believe this estimate, I didn't believe that estimate, but the two of them together getting the same number, that's got to be the truth, right? So he's really going with this.
Why is that one off? What mistake did he make there?
Why is okay? I'll tell you in a minute.
You're wrong. Okay.
Okay. What he did wrong was pointed out eventually by Kelvin's former student John Perry. What Perry realized was that the inside of the that the Earth is not a solid. It's not a solid sphere. There's a mantle inside, which is in some sense molten. It exhibits convection. And so the crust on the outside is like a styrofoam coffee cup. Inside is the hot coffee, and the hot coffee stays warmer a lot longer because of this insulating layer. It has to transmit through all of the heat from the inside has to be lost, has to be reduced at the same time, and it has to all go through this insulating layer. And if you go, I can show the equations. I have the equations here hiding them. But I actually, you can calculate with these equations, 4 billion years. You go from that short time scale, you put in a modern number for the thickness of the crust, and you really get 4 billion years out of that. And so that's part of the mistake that Kelvin made. And the other part of the mistake was that half of the Earth's heat, or maybe it could be more, but at least half of the Earth's heat probably comes from radioactive decay within the mantle and within the crust. And this was, radioactive decay was a novelty in the 1880s. It became a very quote-unquote hot topic of research by 1900, and so Kelvin knew about both things, and he actively argued with Perry, and he actively argued with the people like the Curies who were coming up with the heat from radioactive decay, and he really hung on against all sense for many tens of years. And Perry, by the way, is also famous. He made the first electric car. It's actually a tricycle. It's an electric tricycle, but it was electric and it was a motorized vehicle at the time when there were no such things. And she was. I think this should be used for an internet meme. It's a disappointed Madame Curie. Should be,
We can try to make this happen.
I'm looking forward to that. I think it would be great. So what happened with Darwin versus Kelvin? Okay, there were 50 years of arguments, really 50 years, over the age of the Earth and the Sun. There was a proxy war between their supporters because these were Victorian gentlemen, you see, and they're very polite. But you know, their supporters were not polite. They were screaming at each other, and in the meantime, their work, Kelvin's work, spawned the evolution-based biology and physical geology. I mean, the need was realized. He made geologists realize that they needed to apply physics to understand geology, and so they started doing it, and have been doing it ever since. But all this time, while all of these results were happening, all this new work was going on, Kelvin hung on with a dwindling number of supporters, their heels dug in, their backs against the wall. And here we come to what Kelvin's modern, what people think of him today, how people think of him today. He's Kelvin the curmudgeon. Because while he was a champion to the public and his day, scientists viewed him more as a relic. Although his math helped to make Maxwell's theory of electromagnetism, he never accepted it, he never fully accepted it, and in fact publicly scoffed at it. He expressed reservations about the importance of atoms, he denied the importance of radioactivity, and he even said on human flight, he didn't have faith in any flying except for balloons, basically. He didn't think that they were going to be heavier than air flying. So this is how people think of him as sort of just an old guy, fuddy-duddy. Get off my lawn, kids. That's too bad. Because even this question which Kelvin never got to answer, turned out to be extremely important. What is the age of the universe? And how can we know? We study the expanding universe. Part of this story, I'm sure you know. So first, much later, after Kelvin's gone for a while, they discovered that the universe is expanding. Here's Edwin Hubble. In 1929, he measured the distances to 25 galaxies and compared the distances with recession velocities that he got from somewhere else. And he made this plot and discovered the linear Hubble's law. And he got the slope is Hubble's constant. And this constant is basically a velocity over distance, the slope of that, and some distance is equal to velocity times time. So from this you can figure out how old, from the value of Hubble's constant, you can figure out how old the universe is. There must have been, if it's all expanding, then it must have been a time when it started expanding. And from there, with a modern value of Hubble's constant, you get 14 million years for the age of the universe. And today's best estimates comes from a cosmic microwave background is 13.798 plus or minus 0.037 billion years. The error bars are still a lot of billion years. I mean, you know, that's even more than my age. So you have here. So now we come to our hero of this second half or hero. But George Gamow, who's very important in the development of the early quantum theory. He invented the concept of tunneling. He realized that fusion powers the sun. And he worked out some of the original elements in the Big Bang theory. There's a paper with alpha, beta, and gamma. And as you know, the famous story there being that Alpert was a student of Gamma. They worked together. Alpha really did the whole thing. and then, but Gamma wanted to publish who was already publishing on April 1st, decided that he needed to have a little fun, a little extra fun. He put Beta's name on the paper, make it Alpha, Beta, Gamma, and then and then actually the story goes, I don't know if it's true, but the story goes that Beta was the referee of the paper, and he said, well, I'll let him keep it, okay, because he thought it was fun. And then you have, so then he predicted the cosmic microwave background also, and worked with Alpert and Helmand, and he said later that Helmand, he was mad at Helmand because Helmand wouldn't change his name to Delta. So Gamow was looking at the Big Bang nucleosynthesis, and his idea was that in about the first 15 minutes, well, this is mostly the current idea of most of us now, is that in the first 15 minutes, the Big Bang made well, okay, let me modify this. Yes, okay, sorry. In the first 15 minutes, the Big Bang made most of the visible matter in the universe. That's about 72% hydrogen, 24% helium. Okay, that's now accepted as true. This is a modern picture of how this process proceeded. First you have a Big Bang, and there's inflation, and then there's a quark-gluon plasma. This is the only part of the talk that I actually know anything about. Is the quark-gluon plasma. And then eventually, you eventually get galaxies, and then alpha, beta, and gamma. Okay. And so in this period of time, what Gamow said was that the whole universe was made out of stuff that he called Helium, which he didn't know what it was, but he figured it must be mostly neutrons. And from this, a steady as in the first couple of seconds, maybe 15 minutes, you make all of the elements. And he thought at that time that you would make all of the elements, everything. Okay. So now, what is the evidence of the Big Bang? Okay. And, first is the expansion of the universe. This explains Hubble's laws, and Hubble's law for expansion explains the age of the universe from the oldest and most distant stars. But this is input to the theory. Now, the Big Bang, according to alpha, beta, and gamma, the fusion in the Big Bang would create all of the chemical elements. In addition to that, what they thought was that there would be a cosmic microwave background radiation, and this would be the relic black body radiation from the early hot, dense stage when everything was in equilibrium with everything else. So here we have Gamow, and Gamow said the universe is expanding, the Big Bang made most of the matter. And on the other side is Fred Hoyle, who we'll talk more about. You probably all know about him. He's one of the most famous astrophysicists in the 20th century. Colossal amount of work. He says, well, it only looks like it's expanding, and fusion in stars is what's making all of the elements. Okay? And so, who's Sir Fred Hoyle? He worked on the synthesis of elements in the stars. And you see here, he's completely beardless. I just want to point this out. We're coming into a time when science is free for people without beards. And real advanced, I have to say. So the synthesis he worked on a synthesis of the elements in the stars. His first work was in 1946, and it was only that late because the atomic data tables that he needed, for some reason, were locked up in a closet in 1945. And then once they got done blowing people up, he was able to get the information he needed to make his calculations. And then
there's the famous, his most famous paper was in 1957 on the synthesis of elements and stars, and then he came up with the steady state theory for the universe, which is in contrast to the Big Bang theory in 1948. And he became a Plumian professor of astronomy and experimental philosophy at Cambridge University. This was the same position that was held by, I think it's George Darwin, who was Charles Darwin's son, became a very well-known theoretical physicist. And he was knighted in 1972. And here he is on the radio of BBC, famously naming the Big Bang Theory. People said he was trying to make fun of it, but I think he was just trying to explain it. Okay? It was just, I mean, the idea that there was a Big Bang and all this stuff came about. I mean, that's really the name of that's really what the theory is all about. So the origin of the chemical elements, what did alpha, beta, and gamma do? This is a plot of the abundance of all of the elements. This is as a function of atomic mass up to 250. These are all the things that they've observed. These are the wiggly lines, the observations in the cosmos. The curve is the curve that they calculated in their paper. They were trying to explain all the elements, and so in that paper they did. And the question is, does fusion in a hot Big Bang make all of the elements? Gamma and collaborators said it's possible to make them all step by step. In other words, adding a neutron to the previous element to make the one that's got slightly heavier mass. Okay? The problem is that there's missing steps. There's no stable nucleus of atomic mass 5 or atomic mass 8. So in Gamov's theory, you just can't get past 5 and 8. And he was just sort of, so this is like wishful thinking past here. This is good, and this rest of the stuff, it just happened to work. But you know how theorists are, they get excited. Stellar nucleosynthesis, Hoyle's idea, is that fusion in red giant stars generate the elements from carbon up to iron. Supernova explosions of such stars would then be popped. So iron is the point where you have the most binding energy, and then past that you can't make new nuclei by fusion anymore. So you have least binding energy. I said I get the sign error there. So anyway, and then you get to, and then you start getting less bound nuclei. And how do you make those? Well, the way to make them is in a supernova explosion. Things are very energetic, and they can produce the other elements heavier than iron. And this is from okay, thanks.
Yeah.
So this, yeah, thanks. This, I need to know this, right? Because I can talk all night long. So you know, I mean, so it's the steady state universe after all. So you can go on forever. You have here, so this paper, this famous paper, which also gets a funny name, B squared FH, Burbage, Fowler, and Hoyle, is when they came up with this mechanism, and the explosion not only generates the heavier element, but spreads them across the galaxy. And this is really the cornerstone of the standard model of astrophysics. This is Carl Sagan, you know, yeah, he looks high in that picture, but I don't know. I got it from the internet, so it could be Photoshop or read nothing. But anyway, we are, you know, he said we were made of star stuff. He's thinking of B squared FH, right? And here's a picture of B squared FH. There's the B's, there's F, and there's Hoyle. Okay. And apparently Fowler really likes trains, and so he's using a model train. And he so they they predicted that stars build all the elements, and the only problem is that the elements lighter than lithium, you don't get enough of those in stars because they're too hard to get them bound. Even though you're making helium in the stars, right? I mean, it's kind of almost the way stars work, right? They're making helium. You still don't make enough helium to get 24%. You get 24% of the mass of the universe inside a star. Now, we've made progress, but not enough, because the only one in this picture to get the Nobel Prize for this is the guy with the beard.
She couldn't have weird souls.
Yeah, I know. That's what I'm saying, right? It's just not. But anyways, maybe someday. So Gamow made a he did what a real scientist does. He realized he was wrong. He admitted it, and he admitted it in the form of a joke, which is Gamow, right? So he says, in the beginning, this is his version of Genesis says, in the beginning God created radiation and an island. And he goes on there and says, and God says, let there be mass 2. And there was mass 2, and God saw deuterium, and it was good, and God continued, so forth and so forth. And then he made all the elements, and then realized he couldn't get past 5. And then he said, let there be oil. And there was oil, and God looked at oil and told him to make the heavy elements in any way he could. Very important. The idea that, when you're wrong, you're supposed to admit it is a very important thing in science, right? Because, the evidence, that's the way your thinking evolves. Okay? So now we come to Hoyle's, what Hoyle did, Hoyle's, you call it the evolution of abundances, Hoyle's day job, and you get to the steady state universe, which was another thing that he was a very big champion of. Bondi, Gould, and Hoyle in 1948 came up with the steady state universe. They proposed it as an alternative to the Big Bang. The idea is that the universe is infinite and unchanging, and that there's a steady production of new matter in space between the galaxies that just makes it seem like it's expanding. I don't want to even explain this because it's wrong and it's hard to understand. And so I don't want the thing that you go home with tonight to be an understanding of a wrong theory. Although most of this stuff is all kind of modified with time. The other thing is that's really kind of interesting is that this is sort of like the rebirth of uniformitarianism. Remember from Darwin's old days, right? Now he wants it to be the same without a beginning.
Isn't it true that Einstein held to this theory, and that's why he put a smudge factor in?
Yeah, a lot of people did not want, they did not see a need for an expanding universe until it was measured. And so, and even in the beginning, when the first measurements were made, Hubble's constant was crazy. It was in totally conflict with the age of the galaxies. His constant gave a lifetime of the universe that was much too short, and it took a while before it got to the point where that theory was undeniably correct. And so it was right to have an alternative to that and to entertain it. And this is really quite a brilliant alternative. So the steady state predictions it's sort of built to explain Hubble's law for galaxies and expansion. The expectation would be that the synthesis of the elements is performed in the stars alone. You are making this extra mass to cause the expansion, but it's not enough extra mass to explain. It has to be that we don't see that extra mass. Okay, it's got to be hiding out there. So there must be too little of it to explain any of the abundances. So all of the synthesis elements has to be done in the stars. But there also has to be no cosmic microwave background radiation. There also has to be the distant older galaxies are similar to nearby younger galaxies. Now, this stuff got eroded against for a long time, but it wasn't until the discovery of the cosmic microwave background radiation in 1965 by Penzias and Wilson that it really finished the whole story. Right? This is there they are. They're very happy. They're wearing suits. Here he is cleaning the bird doo-doo out of the antenna up here to make the signal, make sure it's not background noise. And this is, I don't know, one of the great discoveries of all time. So this picture was made by Gamow. It's a picture of Alpert, Helmand, and Gamow, and this is a bottle of Island here. And so now what happened? How did this story play out? Well, evolving versus steady state universe. There are 50 years of argument over the age of the universe. Meanwhile, both astronomy and nuclear physics advanced rapidly. For most of the discovery, the cosmic microwave background finally killed the steady state model, but Hoyle hung on pretty much to the end with a dwindling number of supporters. And what was Hoyle's motivation? Okay, now Hoyle said that one of the things was, I gave many motivations. One of them is just that he's just he's just a cantankerous guy looking for an entertaining intellectual duel, and I think he really liked that sort of thing. But part of it is that one of the things he felt that the reason why scientists like the Big Bang is because they're overshadowed by the book of Genesis. It's deep within the psyche of most scientists to believe in the first pages of Genesis. The Big Bang seemed to be a creation event. Okay? So, as an atheist, Hoyle felt that religion had no place in science, and so the steady-state universe had no beginning, no end, required nothing being created, so that's why he liked it. Okay, or one of the reasons why he liked it. And so who does like the Big Bang? Okay, Hope likes the Big Bang, right? So it's, very early on, the Catholic Church was a very strong supporter of cosmology research. They hosted a number of very influential early meetings in which all this Big Bang stuff was played out. And he actually, here he is, he's saying it right here. He says, that he likes evolution and he likes the Big Bang because it's a creation event, and they're shutting off the power. And so what do I believe? Well, I turn to my Pope. And he says the good thing about science is that it's true whether or not you believe in it. And so I'll go with that. Thanks.
A very brief time for questions. Sorry about it.
Does the convection in the mantle work without plate tectonics, or does it demand plate tectonics for it to work?
It gives rise to plate tectonics.
Okay.
So that's one of the main experimental supports for it.
So, because plate tectonics was widely disbelieved up until like the 40s, right?
Right.
Einstein, 60s.
Yeah. So he was very, to propose that at the time, it was kind of radical. It was more considered to be, the way he considered it was more like let me think of a crazy possibility that's outside of the parameter range that Kelvin was using for his thing. You know, Kelvin felt like, I've got this whole thing nailed down, there's no other way it could be. He says, let me just come up with an extreme possibility. He just thought that it could be that just the thermal conduction inside the Earth was different from the thermal conduction outside. But then, eventually, the only way he could support that scientifically was if it was actually liquid. And, you know, a lot of things have to be true. It has to be that the rocks float on the liquid, that they don't sink down. You know, ice floats on water, but alcohol doesn't.
Right.
And so, you know, you have your you know, you don't know. He didn't know at that time, and then later, plate tectonics came up, and so people were thinking. They were arguing though throughout the 1800s about whether or not the inside of the Earth was liquid or solid, you know, because there's this stuff that comes out of volcanoes, right? And you would think,
Yeah, you'd think somebody would.
it might occur to somebody, but they preferred to think it must be the same inside as it is outside.
Yeah.
You know, it's simpler.
I think we're going to have to wrap up here. Let's thank our speaker again.
All right, so that marks the end of our meeting. We are going to proceed to the grid code. Those of you who are interested in having some astronomy after the astronomy, can go to the grid code tab on Woodward Avenue.
And I also need new members.